Hello everyone, and welcome back. Today we're going to continue our exploration of special vector spaces, and in particular focus on the polynomial vector space of all polynomials degree n or less. In particular, we already have proven that this set Pn is indeed a vector space, and in particular we know that the derivative operator that is typically studied in single variable calculus can be viewed as a matrix on this particular vector space. Moreover, let's just state a couple things before we get started. So we know that Pn is a vector space, and since it's a vector space, you should be able to tell me the dimension of that vector space, and you should be able to tell me with confidence that the dimension of this vector space is going to be actually equal to n plus 1. So if the dimension of this vector space is n plus 1, then you should be able to give me at least a basis for Pm. So one can choose that a basis for Pm can be chosen to be just the unit monomials, in particular 1, x squared, x cubed, all the way down to xn, where n is the exponent on Pn. Alright, so if that is the basis, then of course we can view the derivative as a matrix from Pn to Pn minus 1. Right? So keep in mind that this is a derivative matrix between Pn to Pn minus 1. Right? And at least from previous discussions, we know derivatives are linear operators, so that means that d dx is a homomorphism from Pn to Pn minus 1. Now, you could, of course, say also that d over dx is a homomorphism from Pm to Pn, that is, the dimension of the domain and the range of this particular matrix is the same dimension, and then one could ask, is d over dx an isomorphism? Well, if it was an isomorphism, that means you should be able to invert this particular matrix, right? So for every output of this particular operator on some vector in Pm, you should be able to recover that particular thing. But we do know that, for example, the derivative of 5 plus x squared is equal to, of course, 0 plus 2x, and the derivative of, say, pi plus x squared is also equal to 0 plus 2x, and there's infinitely many more examples that you could give, right? But notice that these two values are the same, but the in particular inputs are not the same. So this operator is not a one-to-one operator, and hence the derivative matrix is not an isomorphism from Pn to Pm. So therefore, we can at least easily construct an inverse homomorphism, say from Pn minus 1 back up to Pn. Right? So those are just some things that we should have constructed up to this point, and if not, that's okay. But now what we're going to do is actually consider a very interesting problem. So we know already, as just mentioned, that the derivative matrix is a homomorphism from Pn to Pn minus 1. And we know that the dimension of Pn is n plus 1. So we should be able to at least think about that Pn and the vector space R n plus 1 share a very important connection. In particular, one, they have the same exact dimension. The coefficients of these polynomials are real. The values of these vectors are real. And we can maybe consider a numerical matrix D that maps Rn plus 1 to Rn. Right? So here's a question that you may want to consider. Well, is it possible to, for example, to construct an isomorphism between these two matrices so that we can sort of go back and forth, right? Now, of course, if we go along each of these rows in terms of this little flowchart, that is not an isomorphism as already discussed. But is there a numerical matrix representation for this derivative matrix homomorphism? And that's one thing that I want to sort of dive into today. because that definitely is going to have a lot of numerical advantages, especially if you want to start developing your own numerical schemes for whatever applications you have. So let's just take a pedagogical example to sort of get our thoughts rolling to sort of see how we're going to map between Pn and Rm minus 1. So let's take, for example, the polynomial in Pn, 5 minus 2x plus 5x squared minus 3x cubed. So I'm just going to pick a particular vector belonging to P3. All right, so what is the derivative of this particular vector? So if we apply the derivative rules, then we should see that this is just going to be equal to, well, the derivative of 5 is going to be 0, but I'm not going to write 0. I'm just going to sort of line up my constants here, my linear term, my quadratic term, and my cubic term there, and I'm going to sort of keep those things there. So 5 is just going to go away, right? And the derivative of minus 2x is going to be mapped to the constant minus 2. So that sort of comes over here. The derivative of 5x squared is going to be equal to 10x, but I'm not going to write 10x here. Instead, what I'm going to write is 2 times 5 x, right? And there's of course a plus sign there. And then what's the derivative of minus 3x cubed? So that's going to be equal to minus 3 times 3x squared, and then we're going to have a plus 0x cubed at the end, right? And what I'm going to do, since we have a 2, a 3, and I technically could put a little 4 at the end here, because 4 times 0 is just equal to 0, we have a 1, 2, 3, 4 coefficient. And notice that in some sense I'm swapping positions, right? And there's no 0 over here, so technically that 0 is swapping from that particular location. Right? So if we want to sort of create a mapping or construct a numerical matrix representation of this derivative, then we have to represent these polynomials as vectors. So what we can do is we can define, for example, this mapping from polynomial space, so the sum from k is equal to 0 to n of a k x k, we can map it to the vector a0, a1, a2, all the way down to an, right? So there's m plus 1 terms here, there's m plus 1 terms in this particular vector, right? So one should be able to show that this mapping F is indeed an isomorphism between the matrices, polynomials, or vectors rather, an isomorphism between these vectors of polynomial vectors in function form and polynomial vectors in Cartesian form. Right? So you can sort of go back and forth if you really, really want to. So for example, if I give you the polynomial 5 minus 2x plus 3x squared, then this is going to be mapped to the three-dimensional vector 5 minus 2 and 3. And if I give you a particular three-dimensional vector, for example, if I give you negative 2, 0, and 5, then that can be mapped to, for example, the polynomial negative 2 plus 0x plus 5x squared. So there's a unique one-to-one correspondence between polynomial functions and these R3 vectors, right? So we have that nice, beautiful representation. So let's see if we can represent this particular problem in terms of R4 now. So if we write that in terms of R4, so keep in mind d over dx is just a matrix, right? But we're going to be representing it in a numerical matrix form. And let's actually define this to be equal to some numerical matrix D, for which we seek to find the coefficients of. So if that's the case, then what do we have? So we have D times the four-dimensional vector 5 minus 2, 5, and minus 3, and this is going to be mapped to the vector. So what was it? So the derivative of 5 was going to be 0, so that, remember, disappeared. And then minus 2 was going to go to 1 times minus 2. 5 was going to go to 2 times 5. And negative 3 was going to go to 3 times minus 3. And then we have 4 times 0 at the very end. And that was the resulting vector, right? So again, notice that we are performing some row swaps, right? So we have some row swapping. And we should know some elementary matrices that do row swapping on four-dimensional vectors into four-dimensional vectors. And we also have scalar multiplication, which are two elementary row operations, for example, from Gauss-Jordan elimination, right? So what is a matrix that will move row 2 to row 1, row 3 to row 2, row 4 to row 3, have a bunch of zeros on row 4, and scale row 1 by 1, row 2 by 2, row 3 by 3 once you swap them into their new position. So what is the dimension of this matrix? Well, we're going from R4 to R4. That means this must be a 4 by 4 numerical matrix. So if you know anything about elementary row operations, then you should be able to tell me what this matrix actually is. So you should be able to verify that this D 4 by 4 matrix is going to be equal to, so 1, 0, 0 sort of moves up into oblivion, 0, 1, 0, 0 is going to move up one position, 0, 0, 1, 0 is going to be scaled by a factor of 2 and also move up, so 0, 0, 2, 0, and then we have 0, 0, 0, 1, but that's scaled by a factor of 3 and that moves up 1, and then we have just a row of zeros and that's going to delete that cubic term at the very end, right? So if this is the case, then here we have a nice beautiful matrix, D 4 by 4, which is going to pseudo map P3 into P2, but moreover it's mapping R4 into R3. But technically, what we're doing is we're keeping this last row because we sort of want to keep this into a square matrix because maybe we want to recover whatever vectors disappear. So since we're choosing a 4 by 4, we're just mapping for R4 to R4. Even if we map from R4 to R3, we still won't be able to construct an isomorphism. So it's just safe just to keep this as a square matrix, and that's perfectly okay. And this is the numerical representation of the derivative matrix d over dx, which maps P3 into, in a sense, P32, except the last term doesn't exist. Because keep in mind, the definition of the set P3 is the set of all polynomials degree 3 or less. So it allows that last coefficient, the highest coefficient of P3, to be 0. Of course, you can change your definitions of your polynomial vector spaces, but of course our notation will slightly change here, right? So this, of course, is my conjectured matrix. You should be able to prove that on your own, but you should be able to verify that this matrix actually works for our example. In particular, if we apply the matrix 0, 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3, 0, 0, 0, and 0 times this vector 5 minus 2, 5 minus 3. So we should know how to do matrix multiplication at this stage. You should be able to verify that this is indeed minus 2, 10, minus 9, and 0, which is the R4 representation of the P3 polynomial result that we got when we just applied our standard derivative rules. Now, although we did choose to take our numerical derivative matrix to be a square matrix, some people will think like, well, is there any problem with just deleting the last row of zeros? And of course not. You just need to change your notations around a little bit. So I just wanted to make a quick note and mention about that. So how would you adapt that? So instead of having that fourth row of zeros, now we're just going to have 3 rows that are all non-zero. And let's make sure that, of course, is a 3 by 4 matrix. You can't do a 3 by 3. You should be able to explain why that is the case. So a 3 by 4 matrix is going to map where to where. So we still have 3 rows, 4 columns, so it's still going to map R4, but instead that's going to map to R3, right? So it's not going to take into account that 0 coefficient on the leading term that sort of disappears, right? And that, of course, is isomorphic to the problem of doing the derivative of P3 and then mapping that down to P2, right? So those are, of course, isomorphic problems to each other. Right? Now, let's take a look at something very, very important. Let's take a look at the reduced row echelon form of the 4 by 4 numerical derivative matrix. So you should be able to verify that, and that's actually very trivial to get. But we're going to get 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and a bunch of zeros at the very end, right? So if we look at this particular matrix, what is the, for example, determinant? right? So we clearly see that this is a non-full rank matrix. In particular, you should be able to verify the determinant of this 4x4 matrix is equal to 0. That means that this square matrix is not invertible, right? And people, of course, would be a little bit sad about that. In particular, why is this the case? Well, if we take this 4x4 numerical matrix and we multiply by the vectors c, a1, a2, and a3, then we're always going to get the vector a1, 2a2, 3a3, and 0. And this is going to be true for any c in the set of real numbers. So we can clearly see that this d 4x4 is not one-to-one, and hence is not an isomorphism, i.e. an invertible homomorphism, right? So in case you don't already know what the definition of one-to-one is, I'll just mention this here just in case you're curious. So a function f is 1 to 1 if fx1 equals y and fx2 equals y implies that x1 is equal to x2. So for example, we can consider the function f, which maps r to r greater than or equal to 0 via f of x is equal to x squared. We know that, for example, f of minus 2 is equal to 4, f of 2 is equal to 4, but 2 is not equal to minus 2, and hence f is not 1-to-1. Right? So f is not 1-to-1, and if it's not 1-to-1, then it's not an invertible mapping. So that's, of course, always a bad thing. All right? So let's state the next question that we want to investigate. So can we partially reconstruct or recover the vector u after this derivative matrix D has transformed u? I.e., can we anti-differentiate a particular vector? So if we write this in equation form, so if du is equal to some new vector u prime, what was u? So let's pretend, for example, that we know D, the matrix, and we know U prime. Can we figure out what U was just based on this information? Well, let's take a look at a numerical example. So if we take the derivative of the vector U, and we get 5 minus 2x plus 5x squared. So we clearly see that this polynomial belongs to P2. So where does that imply that U belongs? So if the derivative sends P3 to P2, and we have an output vector of P2, that means the vector U must belong to P3 because D is a homomorphism from P3 to P2, right? So that means that U must be equal to C, and then we can do some row swapping, but instead of scalar multiplying, we need to do scalar division. So that's going to be equal to 5 divided by 1, x, and then minus 2 divided by 2x squared, and then plus 5 divided by 3 x cubed, right? Where c is a constant that pretty much went into oblivion, right? And you should be able to show that the set of constant functions actually forms the null space of this particular derivative matrix, right? So what do we have here? Well, c obviously is a free variable, which you should be able to, conceptualize at least from the numerical perspective. But what is the matrix that actually has the constant column as the free variable, right? So let's look at this in a little bit more numerical matrix perspective, at least, let's say. So we know that 0, 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3, and 0, 0, 0, 0 times, let's say, u0, u1, u2, u3, the constant linear quadratic and cubic term, is going to be mapped to u0 prime, u1 prime, u2 prime, and u3 prime, i.e. we're just representing this as du equals u prime. So if D is indeed an isomorphism, which we know it's not, then that means there exists some operator, D inverse, let's say, times du, which would give us D inverse times u prime. Right? So if that was the case, then we would have, for example, the identity matrix there. So IU would be equal to the inverse of that derivative matrix times U prime. And that means the solution to our problem will be equal to D inverse times U prime. Right? Now, of course, we know this matrix does not exist, but what we're actually going to do is we're actually going to notate this as A. And A is going to stand for the antiderivative of the operator D, or antiderivative of something, because it's going to be an operator or a homomorphism, just like the derivative operator was. All right? So if that is the case, then what do we have? So one way we can construct this matrix A is consider this particular property that I noted above, right? So notice that we're dividing by 1, divided by 2, dividing by 3. Notice that we can't divide by 0 there, else we have a bit of an issue there. So we're only going to be dividing by 1, 2, 3 elsewhere, and we're just going to be leaving that constant as a free, and some people will even define it as 0 just to be safe. So one formal way we can approach this is via integrals. So if you know the fundamental theorem of calculus, one can show that the integral from 0 to x, for example, of the polynomial 2 plus 10t plus 9t squared plus 0t cubed. Now I'm putting that 0t cubed just as a placeholder, because we know when we anti-differentiate a P2 polynomial, we're going to be bumped up to P3. Right? So that's going to be equal to what? So we're of course going to get 0 in the constant position, and then we're going to have 2 divided by 1 times x, and then plus 10 divided by 2x squared, and then plus 9 divided by 3t cubed, right? And that fills our P3 vector. Right? And of course, notice that if we don't choose a lower bound of 0, would typically be sent to the variable c. Right? And of course, what is going on here? Well, this is of course row swapping, but it's row swapping backwards, and scalar division, or scalar multiplication by fractions. So if we recall our 4x4 differentiation matrix, which is again 0, 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3, and 0, 0, 0, 0, what would be our anti-differentiation matrix, which is also a 4x4? So, using the observations that I already have, if we're just going to send that first constant thing to 0, then the first row is going to be 0, 0, 0, 0. Then we're going to have 1, 0, 0, 0, 0, 1 half, 0, 0, and 0, 0, 1 third, 0. And you can multiply that by the other vector, the vector representation in R3 of that, and you will realize that you will indeed get that particular result. Now again, if you're not happy with, for example, this last row of zeros or this last column of zeros, you can slightly manipulate these matrices to be a little bit more nicer. For example, you can again choose this differentiation matrix to be a 3x4, which would be 0, 1, 0, 0, 0, 0, 2, 0, and 0, 0, 0, 3. And you could, of course, choose the matrix 4x3 for the anti-differentiation matrix to be 0, 0, 0, 1, 0, 0, 0, 1 half, 0, and 0, 0, 1 third. Right? So this operator, D3x4, would be similar to the derivative operator that would send, or the, I guess, anti-derivative operator, which would send, for example, P3 to P2. Nope, that's the derivative operator, right? And the other direction, which would be a 4x3, which is isomorphic to, for example, the inverse operator, or some people will write it as an integral, which will send P2 to P3. right? And those are how you construct, for example, these particular matrices. Now I want to make another point because they're not quite inverses of each other, even if we choose the square versions. So how can you verify that these indeed are not the inverses of each other? So if we multiply one by the other, for example, if we do the 4 by 4 differentiation matrix times the anti-4 by 4 differentiation matrix, you're going to get a matrix that's similar to the identity, but not quite. You're going to get 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 0, right? So that lonely corner 0, is the only thing that's standing in our way of the 4 by 4 identity matrix. And of course, if you do it the other way around, because if A truly was the inverse of D, and we multiply the anti-differentiation matrix by this differentiation matrix in numerical form, you're going to get 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1, which again is not the 4 by 4 identity. But it's close, right? So if we want to apply this to, say, a basic linear differential equation, how do we do it? So let's assume that we want to solve this basic differential equation. The derivative of something is equal to 4 plus 2x plus 5x squared, and we want to use numerical matrices to solve it, right? So in matrix form, numerical matrix form, this is equivalent of saying, okay, we need to multiply this by a 4 by 4 differentiation matrix because this is going to be mapped to P3, which is a 4-dimensional space. And that's going to be equal to the vector 4, 2, 5, 0, which again is going to belong to P3, which is isomorphic again to P4. I guess I should say that belongs to R4, which is isomorphic to P3, right? So if that's the case, that means that our vector, where's my y? That means our vector y is going to be equal to the anti-differentiation matrix, a 4 by 4 times that vector 4, 2, 5, 0. And what is that going to be equal to? So let's recall what that matrix was. So it's 0, 0, 0, 0, 1, 0, 0, 0, 0, 1 half, 0, 0, and 0, 0, 1 third. 0 multiplied by 4, 2, 5, 0, and that's going to give us the vector 0, 4 over 1, 2 over 2, and 5 over 3. Right? Now keep in mind, this is generated from the free variable, so if we don't want that to be 0, we can just map that to be c, but this is true if and only if y of 0 is equal to 0. But generally speaking, this vector, of course, is going to be 0, 4, 1, and 5 thirds, so one can say that the general solution to that basic differential equation is going to be c plus 4x plus x squared plus 5 thirds x cubed, and that's going to be the general solution for that differential equation. And of course, if you have an initial condition, you can find out what that c is. Right? So one last thing before we go, and this is actually something you can think about. How can we apply these polynomial matrices to solve problems like the derivative of e to the x? So if you know single variable calculus, you know that this is just e to the x, right? But sort of, how can we bring this into things that are not so obvious, at least from the polynomial perspective? So if you remember something from single variable calculus, you should know that e to the x has something very special known as a Taylor series, which is the sum from k is equal to 0 to infinity of x to the k divided by k factorial, where k factorial is the product of all of the integers from k down to 1, with 0 factorial being defined to be equal to 1. So in some sense, e to the x is a polynomial, but of infinite degree. So what we're going to do here is we're just going to say that e to the x belongs to p infinity, right? It has infinite degree, right? And of course, we could explore more in detail what p infinity looks like and what a basis of p infinity would be and how to span it and do linear combinations of that. But that's for another day, and we'll just save that for them. Because, in some sense, if we expand that summation, that's just going to be equal to 1 plus x squared over 2 factorial, 2 times 1, and then x cubed over 3 factorial, 3 times 2 times 1, plus x to the 4 over 4 factorial, 4 times 3 times 2 times 1, all the way out to infinity to the power x to the power infinity divided by infinity factorial, whatever that is. But these terms are going to get closer and closer to 0, so you can approximate, right? So if we represent this in p infinity space, that means that e to the x is going to be equal to the vector 1, 1, 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, and so on. So how many rows does this vector have? Well, that's going to have infinitely many number of rows, one column, right? So what is the derivative of e to the x equal to? Well, if you apply our derivative matrix just in infinite dimensions, what would that actually come out to? So we have, for example, an infinity by infinity differential matrix times this e to the x thing, and what is that going to look like? So that's going to be equal to 0, 1, 0, 0, all the way out. Let's actually do another 0 there just to see what it looks like. And then we're going to have 0, 0, 2, 0, 0, 0, 0, 0, 0, 3, 0, 0, 0, 0, 0, 4, and that's going to continue all the way down, right? Infinite number of rows, infinite number of columns, and then we're going to be multiplying that by 1, 1, 1 over 2 factorial. Technically that's 1 over 1 factorial and 1 over 0 factorial. And then we're going to have 1 over 3 factorial, so that's going to be 4 rows, and that's going to continue downwards. Now you should be able to multiply this matrix even though it looks a bit awkward, right? Because there's only one non-zero element in each of these rows, right? So you should be able to figure out which row of this column vector that we're actually multiplying. But you should be able to see that this actually is going to be equal to the same vector that is here. I.e., you should be able to verify that the derivative of itself is equal to e to the x, even if we apply this from the polynomial perspective, which is actually quite interesting. But I hope you enjoyed that little excursion on calculus on polynomial vector spaces. I'll see you in the next video. Take care.